pretty safe, and then it also means that you could view it later again if you really enjoyed it so much. Marcelo, can you start the recording?
Yeah, it's on already.
Excellent. All right. All right. So hello everybody. This is going to be our graduate course for scientific computing for physicists. That's where you are. My name is Ramses van Zon, and I am an analyst at the Scinet Supercomputer Center at the University of Toronto. So is Marcelo. He'll also be an instructor, and we'll sort of take turns lecturing it. So you have the benefit of two instructors. This course has come out of what is now a long tradition of our department to teach people how to use the computers that we have at our disposal in the best possible way. Most of you, I assume, and might want some feedback later, are starting graduate students. And both Marcelo and myself have been graduate students and have had to learn the things that you are going to learn in this course by trial and error and by making many mistakes. And so our aim is to make these mistakes unnecessary for you to make again. So learn from us. So a few things that we're going to do in this course particularly is there's sort of three main themes. And they kind of go in this order, but not entirely. We're going to look at scientific software development. So the idea is that this is really a course for people that are either developing their own code or maintaining a code, or at least want to know how that is done. And so we're going to go into that and look at that from a perspective that is typical in scientific research. And so that is a slightly different focus than other software development, but a lot of them are overlapping. So those are also good skills to have, just generally if you ever go into software development. Another main theme, and this is how it fits into the physics program, is that we're going to focus quite heavily on tools, numerical tools that you can use in physical research in particular. So a lot of code has already been written and you can use it. Those are called libraries. And so we're going to look at a whole bunch of them, very common ones that you will want to know how to use. And so that's going to be the second theme. And then finally, we're going to look at high performance scientific computing. So this is the point where you're not just using the computer because it is convenient. You're using it because you want to do things that aren't possible any other way. And often that means that you want things done as fast or with as much data throughput as possible. So that's the realm of high performance scientific computing. That's where profiling and tuning becomes important. That's where parallel programming becomes important as well. So we'll look at that in the third part of the course. So that's what we're going to look at. What's going on? I already introduced myself and Marcelo. There's a TA for the course. There will be assignments. And so this lecture is going to be partly just explaining about the course, which is good to do. And then we'll head into the actual topics. TA is Camille. He's been with us for a few years, so he's quite knowledgeable about the whole situation. He's taken this course as well, so he knows what it's like to be on your end as well. So as I said, we are from Scinet. Scinet is a special department in U of T that hosts and supports supercomputers, but most of its staff is actually has a research background, and we do a lot of teaching. This is one of the things that we teach. We also do a lot of training. So those are, let's say, events that aren't for graduate credit per se, but could still be very useful. So we teach Linux shells, Python, R, some GPU programming, databases, a whole bunch of things. I hope you've all found the education website, although we send the link to this Zoom meeting directly as well. If you haven't, they're all listed on there, and they're continuously updated. We try to book it one term ahead, but sometimes we add things on the fly because of demand. So that's us. So here's the course website. Here's the short link to it, courses.scinet.utoronto.ca/545. On that site, you will find the lectures, the recordings, the slides. You'll find the assignments. There's a forum where you can ask questions. We will give these assignments on Thursdays for the most part, and hopefully for the whole part, but things happen. And then you have a week to do these. And then if you're going to take this for credit, and most of you are, make sure you've signed up in Acorn for the course. It's not instantaneous, so we might not see your name. If you signed on today, we don't see it yet because it has to go through Acorn, and then to Quirkers where we can see it a day or two later. So if you're in a hurry, just email us and say you've registered, and we'll make sure that you have access to everything. So that's the course website. It'll be very central to what we're doing. We're not using Quirkers. Part of the reason is that this website predates Quirkers, and it can do everything we want it to do already. So, which is a good enough reason. So let's go back a second. So that's us, and that's the website. But I think it would be nice to know who you guys are. Now, we're a little bit too big of a group to all take turns saying what we are, but it would be nice if you could say in the chat, perhaps, what your field of study is, or your field of what the program you're in, and what you hope to get out of the course. Another thing, so let's do that first. And so just, it's not mandatory, but it'll just be nice to know, what our audience is. I expect a lot of physicists, but it's an open course, so it will be good to know if there's other people here too. Don't be shy, just I'll type my background. Seeing some engineering, I'm seeing some atmospheric physics, I'm seeing high energy physics, condensed matter, general relativity, in the math department. That's interesting. We've got a chemist there, fellow chemist. Hey, atmospheric physics, chemical engineering, astrophysics, yes. Another engineer. More atmospheric physics. Yeah, so far I'm seeing fields that are heavily computational, or at least can be. So you're definitely in the right spot. Yeah, biochemistry, molecular dynamics simulations, astro. Yeah, nice. Geography. Yeah, physical chemists. That's nice. Thank you, guys. So that's great. It actually sounds like you're in the right spot, and in that it's likely that you'll be able to use the things you learn here for your research. Another thing that can be useful just for us to know in advance is that, in principle, you're supposed to know a little bit of programming to be able to do this course. And the reason is that we're going to be programming, but programming isn't the objective of this course. It's teaching you how to be more effective in it. So it would be good to know what kind of programming experience you guys have. And so let's start with a simple question. what programming language have you used? Just type it in the chat. C++, Python, R, BASIC, Pascal, Java, but whatever you have even just played with. It'd be nice to know what people have done. Oh, there's more BASIC than I had imagined. Yeah, I started in BASIC too, but I am an old guy. Okay, so that makes sense. There's a few people whose main programming language has been Python. If you haven't done a compiled language like C or C++, Fortran, Java, and this is just to be honest, you're going to have a little bit more work to do in the beginning part of things. We're going to use C++, and C++ is a very complex language, and that's not why we use it. We're trying we're using C++ because it's a compiled language, and I'll explain in a little while why that is, for our purposes, a better choice than, say, Python. But we're going to keep the complexity to sort of a bare minimum of what we need to be able to do. If you're a well-versed C++ programmer and you want to do the assignments and use all of your tricks, that's fine, although we might say that your tricks are too complicated, but that's just feedback we like to give in general. But the point is there's only a sort of subset of C++, what we call C++ Lite, and that's actually kind of what we're going to discuss the first the first few lectures. That sort of basic level of what do we need to know to be able to do the assignments. And assignments will be tailored such that you should be able to do it with just that basic knowledge. Yeah, so that's that, and you know, that's a little bit, as I said, it's going to be a little bit more of a learning curve for those of you that haven't done that, but we're here to help. We will have office hours. You can email us, you can use the forum, and I'd encourage you to reach out. Sometimes, because we have been working in these languages for so long, we don't realize something that is trivial to us can be just not clear at all for you. And that's on us, but we can't know that we've made that mistake unless you ask the question and go, oh, yeah, that is a valid question. There are very few stupid questions. So the only stupid questions are when you really try to make a stupid question. If you have a question, it's not stupid because it's a question. Okay, so that's going to be our aim then, is to try in this first, say, 2 weeks to get people kind of on a similar basic level if they're not already there. And so one thing that we're going to do to help out with that is to, although it might seem that that's not exactly helpful, is to ask everyone to use our teaching cluster. So we have a teaching cluster at Scinet. On the teaching cluster, we have the compilers installed. We have a few very basic editors, but they work. And what that will do is, as soon as you are able to connect to this teaching cluster, and we'll give you an account for it if you don't have a Scinet account yet. As soon as you are there, then everybody has the same environment. One of the things that we could do when we were doing this live and not online is we could have people do the assignments on their own computer. Every computer is different. Not just the fact that you have Macs, Linux machines, and Windows. The way you install the compilers could be different. But in an era when people could come into the office hours with their laptop and show us what isn't working, and we just help them fix them, that was okay. Right now, we can't do that. And so it'll be much easier if everybody has the same environment. And so that environment is going to be the teaching cluster. So we will give you a temporary account if you have no Scinet account, and you will know if you have no Scinet account because if we have given you an account that starts with TMP underscore for the education site, then that means that you didn't have a Scinet account. If you had a Scinet account, you would have logged into our education site with that account. The Scinet account is the same as the Compute Canada account. They're essentially the same. If you have a Scinet or Compute Canada account and you have a temp account nonetheless, something went wrong, let us know. It'll be much easier to use your actual account. I mean, the fewer accounts you have to juggle, the better, I find. So that account, that TMP account, is not valid on the teaching cluster. On the teaching cluster, we'll give you a new account, so you'll have two accounts. If you have this Compute Canada account, we can make it work on both, and so that's easier for you. This username for the teach cluster, we have to assign that, and so what we'll do is that tomorrow morning we'll see who's already registered, because most of them will have made it through this whole registration process, and we can assign the student accounts for the teach cluster. And so as that is then ready anyway, we will have office hours tomorrow at 2. If you can make it, I would suggest joining us, because not only will we then be able to give you your account right away, I will also show and demonstrate how to log in and maybe sort of get rid of the first hurdles before we actually have to start an assignment. Okay? So if anything here didn't work for you, you either don't have a way to log into the education site, or your TMP account, you've gotten it, but you can't log in, or any other issue that isn't clear, either ask us now or email us. The way to email, well, I have the contact information at the end, so let me not skip over that. But there's an email address you can just write to, and we'll sort it out. Okay. We will do assignments. The first assignment will be set on this Thursday, and you'll have a week to do it. And so the idea is that you'll do it on the Teach cluster. If you want to do it on your own computer, that is not forbidden, but it will have to be such that it works on the Teach cluster. And so you should at least have tried it on the Teach cluster, even if you did your homework not on the Teach cluster, and it better work there. I mean, that's, yeah. Yes, Marcelo pasted the email address to the chat. So now this will work for the course. These temp accounts and these PHY1610 student accounts for the Teach cluster, and that is fine. That is all you need. If, however, after the course you still want access to the supercomputer, and it kind of sounds like most of you will at some point want that, you could get a Compute Canada /Scinet account, and here's the link to how to get that. By the way, the slides are on the website as well, and the way the website works is you actually don't have to even be logged in to see things, but you will have to be able to log in to submit assignments and to see the Zoom link. So, but all the material is accessible regardless. Okay, so these assignments that I was talking about are going to be near weekly to keep it simple for averaging, and also because the workload can essentially only be so much. We'll have near weekly programming assignments. There'll be 10 in all. They're always due the next week. The idea is that, well, you can of course talk to each other and help each other out. That's okay. We expect original work from each student, like, so that we are not doing team programming. That is hard enough in a live setting. We just need original work, and we will do a cursory check on that. Most years, I wouldn't have to say this. Occasionally, something funny happens, and I just want you to know it's expected you do your own work. The average of the assignments will make up your grade, so there won't be a midterm, there won't be a final exam. We just have to have the assignments. It is expected that you've done all the assignments to have a passing grade. So we need 10 assignments. Now, that assumes that you'll hand them in all 10 in time. We have a policy for that. You can be late. That is allowed, but there'll be a penalty. So every day that you're late, the homeworks are typically graded out of 100. You lose 5 points, and that's up to a whole week. And the reason to do such a firm cutoff mostly is because these assignments are somewhat cumulative, and so we will need you to have done an assignment to be able to do the next assignment, and that'll just completely break if we don't put a cutoff. If there are exceptional circumstances, like always, obviously you can ask and let us know. The only exceptional circumstance that we do not allow or do not allow for is that you say, well, I was busy with other assignments. That unfortunately we can't really see as a reason to make exceptions. But obviously, if you're sick or something happens, if you couldn't submit because your internet went down that day, those kind of things, just email us and we'll try to be as reasonable as we can. But we do expect every homework to be submitted at some point. If it's such an exceptional circumstance that you couldn't submit or you missed one, we will allow a makeup assignment at the end of the term. And if it's very, very exceptional, that is just a discussion with us, right? But that's it's not that happens, and that is fixable. Okay, so you should try. Don't count on this makeup assignment. You should try to just do the assignment, hand it in on time, and then you'll follow along nicely. Ask questions if you're stuck. The course works best if you try to engage with either us or your fellow students on the forum to hone your skills. Okay, now this slide should be almost obvious, but the lectures are through Zoom. You're all here, so that worked fine. We'll put the Zoom link on the course website. The one that is there today might not be always the one in the future, so just check it. The way that the Zoom has been set up by U of T, and I think that is sensible, is that you have to enter a password to get in. So we should be fairly safe against Zoom bombing. And because you can't see the Zoom link if you're not logged into the education site, that should be fairly safe. We will record the lectures. We'll post them on the site. Sometimes it takes a little while to post-process, but by the end of the day, it's usually up. And then that's the lectures. The office hours, we have 2 slots set aside. We found one slot doesn't always work for everybody. So there's a Wednesday slot from 2 to 3, again over Zoom and with the link on the website, and one on Fridays from noon to 1 p.m. So that's where you can ask questions, standard, like we will be available live there. And since the assignments are due on Thursdays, the Wednesday one is very nice, but know if you can make it, and then work ahead so that you have your questions ready on Friday. If any other questions, you can use the forum on the website, or you can email us at courses@scinet.utoronto.ca. So there's one email. Both Marcelo and myself are getting it, as well as some other Scinet instructors. But yeah, or if you have something to say that shouldn't go on a forum, you don't want the other students to see it because it is a private matter, again, email us at courses@scinet.utoronto. We've started making lecture notes last year. Something happens, I don't know, COVID. The lecture notes aren't complete, but they are actually pretty good for the beginning part of these lectures or of this course. So it might be useful to know that this link is there. If you want to read a little bit more than just the slides, it has a little bit more in-depth stuff. So it's just an extra resource if you want. Okay, so that's the course. What are we going to do more in detail? So as I said, there are these three themes: scientific software development, numerical tools, and high performance computing. In the first part, we'll focus on C++, like the C++ Lite that I was talking about, and we'll look at some things that are extremely useful, but in the long term, and by long term I mean more than a week, really. Um, of software development. So modular programming, we'll look at automating software building. We'll look at objects, arrays, version control, unit testing, and some I/O. And that'll take us about 4 weeks of the 12 weeks we have. We'll then focus on numerical tools using libraries, and then libraries for differential equations, partial differential equations, Fourier transforms, random numbers, Monte Carlo simulations, and some molecular dynamics. So here you can really see sort of the bias towards physical sciences. And the focus on this in this part is really for you to program less and use other people's code, but use it wisely and know what's out there. And then finally, the last part is the high performance. So we'll look at how to figure out if your performance needs any tuning or can use any tunings or profiling. And then we'll look at different ways to do parallel computing. So much of the initial part will be using, when we have a code, it will run on a single core of a machine. Most machines have multiple cores these days. The supercomputers all have multiple machines linked together. The only way to do that, to use that, is to use parallel programming. There's no automated way to utilize those. You have to program that, and we'll look at how to do that in the last part. Okay, so that's about the course. So we're about to start our scientific software development area. But let me stop here if there are any questions about the technicalities of the course or otherwise. And actually, most of these details, or well, hopefully all of them, are also in the syllabus, which is also on the website. So you can read them there, but or on the slides. Okay, if there's no immediate questions, feel free to ask them later. That is fine. You know, that I don't mind that. Okay, so let's look at scientific software development. So that's our first area. And so let's start just talking about what we're really after here, what we're going to do. We're going to be doing a thing called programming or coding or scripting. Although when you're using C++, you should never say scripting. People get very offended. So what are we going to do? We're trying to have the computer do stuff for us, right? So, and we kind of have a good idea of what we want it to do. So we want it typically to perform a whole bunch of computations, and they're typically very similar. Either they're data manipulations, you read in data, you sum them up, or you do something else with them, or you're simulating things, but then maybe you have a grid, lots of points, every point has to be treated similarly. There's a lot of computation to be done, and that's why you would use scientific computing. And so programming consists of specifying exactly what the computer should do. Now, the way to think of that, and the way that the computer really does this, because there's different ways to do programming, but what mimics kind of what happens in a computer is to think of the computer as having some sort of state. There are values that it holds, often in memory or on disk, and then there's actions that are done on that state. You could also think of the state as working data, but that's kind of the idea. You have a state, there are some values that it remembers, whatever they represent, and then you specify by programming what actions you should do. And the reason that is a task that we as humans have to do is that there's a limited set of predefined actions. And so depending on the level of your programming language. And this could mean you're actually know the actions that every chip can do individually. Then you're programming an assembler, which almost nobody does anymore. Or it could be high-level actions like you have in Python, where you can open a file, you can fill a list, you can print a list. But still, there's a limited set of predefined actions, and we want to do something like to sort of build a new applications out of these definitions. And so we have to express every one of the actions into these predefined actions. And that is really what programming is. This takes a very imperative view of programming, and I realize that, but it is the way that is sort of closest to what actually happens. There is a memory in your computer. It holds values. The CPUs, the chips, are actually, they have instructions, which are actions that are done on that memory or on local memory on the chip. And so that's not a strange way to program. It is a very natural way to program, and figuring out how to express very exactly the things that we want to do. That's what we're after here. Okay. Okay, so I'm just defining a few things here so that we are all speaking the same language. One often hears about algorithms. Algorithms is a common set of actions to achieve a net effect, but it doesn't have to be programmed in a specific language. Algorithms existed before computers existed. If you want to know how to take a square root of a number, there is an algorithm for them, and you can do it with pen and paper, and it'll tell you all the computations to do. That's what an algorithm is. Okay? It's not code. And it's a specification of what actions to do, and usually on a higher level or a pseudo language or something like that. If you're talking about code, we will have to implement these things. So we'll have to implement an algorithm, and then it becomes often a function or a procedure or a subroutine. That is a set of actions that can be used, but the reason you put it in something called, say, a function or a procedure or subroutine, those are reusable bits of action. So you've written it in a certain language, you put it in a function, you can call that function repeatedly. And remember, that was a typical use case, right? We have, say, a grid of points or a set of data. We want to do the same action on this and each. We can use that function rather than having to type in 100,000 times the same actions. We just type it once and we reuse it for every data point. So those are reusable bits of action. A program, also called an application or an app, or if you're using higher level languages, sometimes called a script, that's a function you can execute, which means that as a user, as somebody that's in front of a computer, I can either click on it or type its name, and it will run, and it will do whatever it does. It can contain several functions or procedures that it uses, but the program is the thing that we run separately. They can have some external data that we give and produce some output. So there's input and output. This can be input on the command line. It could be input on disk, various ways. Okay. So let's think a little bit about state again. For the most part, program state is stored in computer memory. Okay, and most of that, or well, not necessarily most, but often most of that state has a name. So every value has a name, and when it has a name, you can call it a variable. So when it has a name, it's a variable, and the variables are really values that you can think of it as little boxes with a name, and I can put a value in it. And they're called variable because I say I have a number 1 somewhere, and I give it a name x. In programming, I can change that value of x to 2 because it's variable, right? And that means I'm assigning the value to x. So different from sort of a math background, and one or two of you had a math background, where once a variable has a value, once a symbol has a value, x equals 1, it can't also have x equals 2 at some other time. It is already 1. That's not how variables work in programs. They can be changed. Okay. And so the state can change and the variables can change. But this variable in the end is stored somewhere in memory, and that holds the variable's value. Okay, so oftentimes we can just think of program state as the variables that the program has and what it does with them. or to them. Now, we don't always want to do the exact same computation, or the algorithm might have something that says, if your value is less than 1, do this, otherwise do something else. So you need control structures to do if statements. So control structures perform different actions depending on whether something is true or not. Another control structure, which is also sort of conditional, but in another way, is called loops. Loops essentially are repeated actions, but that are counted or enumerated in some sort of way. And we'll see later how that works, but it's a repeated set of actions until you're done. Say you want to go over a list, you have to repeat it until you're done with the list. So that's a loop. Now, these are all very general ideas, and they've been around for quite a long time. So this was written down in 71, but it was true even earlier than that. The point is, this is still true now. There are things that you can put on top of these basic ideas of programming, but we will not insist on having those necessarily. There's things like object-oriented programming, there's functional programming, there is generic programming, all of which are sort of on top of this. But at the end of the day, behind the scenes, it's still all loops, control structures, variables, and state that has to happen. And so if you're coming from Python, you will be able to fill in what all of these different things are in Python. A loop will be a for, a conditional will be an if, a variable will just be we've already called it a variable. If you're coming from C++, you will also recognize these things. So every language has these things in them if it's an imperative language. I'm not talking about functional languages here, sort of on purpose. So that is the kind of things that we have to be able to do in C++. And so we're going to go over them in C++ and see how we do them. But yeah, so that's kind of our program from now on. So these are the things that we want to be able to do in programming. Now, how do we do them in C++? Now, nobody asked why we're using C++, but I think it's worth pointing out because, to be honest, if we could do the things that we are going to do and we could do them well in Python, Python is a lot easier to learn. It's a high-level language. Why are we using C++ here? And so there are big advantages here. One of the biggest ones that we find, and why you find people using it on supercomputers and computationally heavy applications, is its high performance. And that has to do with the fact that it's a compiled language. So you will give a piece of code to a compiler, and it inspects it and optimizes it and translates it into machine code. Now, Python does that too. So that Python is on the other side here, sort of. Python does that too, but it interprets every line and it misses a lot of opportunities. So it's less high performance, much less in some cases. So high performance is one of the reasons for using it. The reason you can get that performance is that it is possible in C++ to do low-level programming. You do not have to, but you can, and so you can squeeze out sort of the last bit of performance that your computer can give. It's standardized. It's ubiquitous. Like you can find C++ compilers for almost any platform. It has a useful set of libraries, and it has a modular design, which means that we don't have to rewrite a whole code with every action every time. We can reuse parts, and that's going to be very useful. Disadvantages of C++ are that it is very precise. What you give to the compiler has to be exactly right. And so you will get error messages that the compiler doesn't like your code. It doesn't even try to run it. And so that means it is somewhat more labor intensive. It is error prone, and that is true. So that's the price we pay. You can do high level programming. In fact, if you're doing C++, and you follow a standard like C++17, there's a lot of high-level programming you can do where the code almost looks like Python. It is not, though. Like it looks so. But you can do it. You don't have to. It's kind of up to you. It's non-interactive, so you can't get a C++ prompt and just try something out and inspect the result. And that is an advantage that Python and R and other interactive languages like MATLAB do have. Graphics is not very portable. Like, it's not that you can't do graphics in C++. People write whole games in C++. Obviously, you can do graphics. But if you had that graphics written for, say, a Windows machine, and now you want to run it on Linux, you might get some trouble. And there's no standard library that will do even a simple scatter plot. So that's unfortunate. And because some of the high level programming is up to you, while it's high performance, there's ways to hide performance costs, and so you have to be aware of certain performance pitfalls when you are doing high level programming in C++. So those are disadvantages. We're gonna have to go towards high performance, and so rather than splitting the course and doing the first half in Python and the next in C++, we're just doing C++ throughout. That is actually easier. As I said, I mentioned Python a lot because it was in the answers, and it's very popular. A lot of the advantages are reversed. So it's less labor intensive. It's easier to write or express what you want. It has a lot of high level programming in it already. It is interactive. Graphics, if you use matplotlib, for instance, it's very simple in Python. Python is also modular, so that is absolutely an advantage that it has as well. But even in Python, there's lots of performance pitfalls. When I'm doing my Python course, I have a Python training course on HPC Python. And I always started with showing the difference between C++ and Python for a scientific computing. And depending on the machine and the compiler, etc., Python is often like 100 times slower. And it's a real thing. And while you can do some things to make it better, that 100-fold speed up is a good reason to try and use C++. So that's what we're doing here. We want all the way from basic applications to high performance. We're going to use C++. Okay, so we've got some questions here. Yeah, we're going to look a little bit at compilers and IDEs and stuff. And I have a few things to say about that, but yeah. Finally, as a note, you can write bad code and unperforming code in any language. I can make a C++ code that is 1,000 times slower than a Python code, but I really have to try. Okay, but you can do poor things. So it's not a matter of which language is better or clearer or something. It's which language is better for our purpose. And our purpose with scientific computing and computationally heavy workloads, C++ is a good choice. Fortran would also have been a very good choice. It was just too much to do C++ and Fortran in the same course. But a lot of the things, particularly because we really try to restrict ourselves to sort of C++ Lite, will translate almost immediately to Fortran. So while the syntax is different and some of the compiler flags might be different, the general lessons translate right to Fortran as well. So that is we just choose C++ just because. I guess I do more C++ than Fortran. It's good if your instructors are more knowledgeable about the topic, right? Okay, so let's look at C++ then. I already said this, but C++ is a continuation or built upon C. Those both are compiled languages, as is Fortran and as is Java. What happens is that their basic actions get compiled into a basic set of native instructions. So that's not entirely true for Java, but it is for C and C++ that the processor can execute. Okay, C was designed for system programming, and so that is a real low-level, fairly low-level language. It has a very small base language, which means it's actually not that hard to learn completely. Whereas C++, there's very few people that know all of C++. Like that's almost impossible. For C, it's almost possible. A lot of the functionality in C was always hidden in libraries. So if you wanted to write to screen, there was a library for that. If you wanted to compute the square root of something, it's in a library. It's not part of the language. C++ builds upon that and tries to improve some of this very low-level stuff, and we'll just be using that because it's more modern. And just to be definite in terms of what level of C++ we're following, because C++ is standardized, but they keep updating the standard. We're following the standard from 2014. You might think that that is hopelessly outdated, but the way that these standards work is they are set in some year, say in 2014, and then it takes compilers a few years to catch up and actually be conformant to that standard. There is a standard from 2017, which is almost in all compilers, but not in every one of them. And so that's why we just say, well, let's just say C++ 14. Most of what we're using could be used even in C++ 99, like 1999, like that. That's. But if you're writing code and you're using C++ 17 structures, we'll ask you not to. Okay, this to make sure that we have sort of a standard, just because the compiler might not be able to handle it. So C++ 14 is fairly universally supported in all compilers, either on your own computer, different computers, and supercomputers, etc. So let's look at a very basic program, and the most basic way that we would like you to try and work with C++. So here's a little program, and we'll explain what it does in a second, but it illustrates a whole bunch of typical C++ isms. And this code is supposed to go in a file. The file will be called hw.cpp. .cpp is one of the most common extensions used for C++ code. Doesn't have to be. I like just CC because it's one character less to write or to type, and I'm a lazy typer. But CPP is a little bit more common. And if we wanted to, say, run this on the teach cluster, there's a few steps to take just to get us there. And as I said, we're going to expect you to do the assignments on the teach cluster. So this is how you would do it. You have to connect to this teach cluster. Now, you would do that. The teach cluster, as most supercomputers, only work, not only work, mainly work either on a terminal command line or even just completely offline. So submitting a script that runs without you interacting with it. So that is something that you might not all be familiar with, but it's something that you're going to do in this course. So if you are able to open a terminal on your own computer, and I have some hints for that in a second, then on that terminal, you can connect to the teach cluster using the SSH application or command. So on Macs and Linux, that's typically already there. On Windows, you can use an application called Mobile Xterm that can give you that capability. Open a terminal, and then you type SSH, your username. My username is Arson, and then @ this is not an email. This is just saying this user wants to connect to this machine called teach.scinet.utron.ca. It will ask for your passwords. You type it in, and then you're in. Once you're in, you would want to compile this, but you need a compiler. And for that, on the teach cluster, you have to do this special command called module load GCC. GCC stands for the GNU compiler suite, compiler collection. And so it'll include G++. If you don't, the command that you need to use to compile, which is called G++, is not available. So we just do that, and then we have our command available. It doesn't install it. It just makes sure the compiler, so the operating system can find it. Now we have to create this file. Now, everybody has their own favorite editor, but we're in a terminal here, and so we should use an editor that can work in a terminal. And there's a few very standard ones. VI is one. If you like VI, use it. Emacs is another one. If you like Emacs, fine. I'm not going to go into a debate which one is better, Emacs or VI. There's a clear winner, and I won't tell you which one it is, because everybody has their own opinion. If you don't like any of them, if you haven't worked with any of them, a nice one to start with that is a terminal-based editor is Nano. It's nice because at the bottom of the screen, Nano will tell you all the commands. It will tell you how to write a file, how to open a file, how to exit Nano. Whereas VI and Emacs, once started, you'd have to Google how to get out of it. So that is one funny little snag. So that's assuming we're just staying in the terminal for now. Emacs also has a GUI, but that's not here or there at this point. We start the editor, we type this stuff in, we save, we should have a file called hw.cpp. And then we compile it with G++. And I see some questions, but I'm going to go through the whole thing first and then look at the questions if you don't mind. So G++, we want this to compile with C++14 standard. So this little argument does that for us, dash std equals C++14. Doesn't really matter for this case, but it's good to have it in there. And then we want to write it out to something. So we can give an output, dash ohw means that our output, our executable, is going to be called hw. And this is our source code. So our source code is going to be converted into machine code. That's going to be hw. Then I can run that hw by ./hw, and it actually will print out hello world. That's what this does. You'll also have something else that it will have given us. There's a 0 here that is returned, and that actually is visible in this special $ variable in the shell. Now, that's a lot of things, and we're going to go over these in more detail. This is not, if you've never seen this before, I don't expect you to know everything, but this is the most basic way we are going to be using C++ in the teach cluster. Okay, so let's see what the questions were. Okay, there's some people having trouble logging into the teach cluster. We'll solve most of these tomorrow. Like we can do two things. If we can't solve it now, email us, because it might just be a matter of us giving you access to the teach cluster if you have a Scinet account. If you have a temp account, that one will not work. So if you try to log in with tmp_, those are not valid on the teach cluster. You need a separate account, and we're going to assign those tomorrow morning when we have a fairly complete list of everybody that's registered. Okay, so we'll make that work. As compilers, there's very many different compilers, but that's why I want something that follows a standard, right? On the teach cluster, we're gonna have you use G++. We also have Intel compilers. That's fine, but in this way, the Intel compilers are not free. You can get free versions, but they're not entirely free. The GNU compilers are. So if you ever wanted to port what you did on a teach cluster to your own machine, you can download G++ and get that working, and it works the same. So that's just to keep it a little universal. If you're working in Visual Studio, then you'll have to use the Microsoft compiler and figure out how to specify the standard. If it follows the standard, your C++ code will work. Let's see what else. So these are all meant, so there's some questions about editors. Oh, and then a question about the output. Yeah, so if I don't specify -ohw, because it's an optional thing, it will create a file called a.out. So a.out. And that might be fine, but then I have to invoke it with ./a.out, which again is fine. But if I'm compiling anything more than one thing, it's good to have it have a reasonable name. So that's what this does. If I don't specify the standard, there is a default standard that G++ will use. It varies from version to version of G++, and so that's another reason just to be specific, but it is optional. So doing G++ and just the name of the file would have worked, most likely, would have created a different file that I have to then invoke instead of HW. Okay, now if command lines are new to you, That's okay. We're not going to use a lot of command line stuff, but some. So we're going to have a couple of training sessions that you might either want to attend or look at the recording of afterwards. The first is tomorrow. That's an introduction to Niagara. Niagara is our bigger supercomputer. It's kind of set up similarly to the Teach cluster. So there's a lot you could learn by following along, even if you have just a temp account. Because you'll be doing very similar things on the Teach cluster. So that's nice, and that's tomorrow at 10. If you want to sign up, and you'll have to sign up to see the Zoom link. It kind of works the same as for this course. You can do that at this link. And then next week, there is a 3-hour intro to the Linux shell. So that, if you're really new to Linux shell, I really recommend taking that. You do not have to have access to Niagara. You just have to have a Unix shell. By that time, you will have figured out how to get that, and it'll sort of teach you how to use Linux or Unix. In I guess in 3 hours, not in 2 hours. I highly recommend it if this is your first time working on the Linux shell. Just as a reference, and just so you understand what is happening before you take that course, here's a super short intro to the shell. I shouldn't do this, but I'm doing it anyway. And then we'll stop after this and continue on Thursday. There's a prompt. It will look differently in every shell. And after that prompt, you can type in commands. So that you need a keyboard or like. And that command is then interpreted. So there's a shell interpreter, that's what it's called, and it takes that command. And there are different shell interpreters. The Teach cluster uses a thing called bash. It's very common on Linux. So if you ever need to Google something specific for the shell, you might want to specify bash. Another thing, you're always in a directory. You start in your home directory. You can change the directory by using the cd command. And there's some shorthands to know. Twiddle or tilde or whatever you want to call this is a shorthand for your home directory. Dot is a shorthand for the directory you're in. And dot is a shorthand for the parent directory. So directories contain directories, as I'm sure you're aware, or folders contain folders. Same thing. If you want to go up, that's dot. Commands are either built in, so things known by bash in this case, or they're executables that are somewhere in standard locations. So standard locations have to be encoded in a specific variable for it. If they're not, you can't call them unless you specify the path to those executables. So for instance, if we had our HW executable, we couldn't execute it by saying HW because it's not in this special standard location. It was in our own directory. But if we prepend it with /, then it says it's in the current directory, execute it. Another example of a command was SSH. SSH is in the path, so we don't have to specify the folder. After those commands, you can have more words typed. Those are called the arguments. So our std equals C++14 is an argument. -o HW was an argument. The code, the file name of the code itself, also an argument. What they do depends on the argument. So they are just given to the application, and it does with it whatever it wants. So that is not universal at all, but that's up to the command. So I'll end with this slide of tips on how to get a terminal shell, but I've already mentioned this. So Mac, Linux, you have it. Windows, try to get made by Xterm. It's the easiest one to use. For editing code, again, I said VI, Emacs, Nano. If you want to use your own local editor, there is a way to do this, but it is not entirely trivial to set up. But Google what SSHFS can do for you. And that can help you not having to constantly copy over files to the Teach cluster, but edit them sort of in place on the Teach cluster with your favorite local editor. Don't be afraid to try out Nano, though. It's a pretty easy editor to use. Okay, so I'm going to stop here. These were never meant to, like these 63 slides were never meant to all be gone through in one lecture. So let's not worry about that. But this is supposed to get you started. I'm hoping to see most of you tomorrow around 2. So we can give you your account on the Teach Cluster. We can demonstrate how to begin. You can try it, and if it doesn't work, we can try and make sure it works. Because we will be giving you a homework or an assignment on Thursday, so you will have to be able to get onto the Teach Cluster then. So, any last questions before we close this lecture?
Sorry, that meeting tomorrow, is that through Zoom or is that?
Yes. So we'll post a link on the same spot where you found the link today on the education site.
Thanks.